Here is the contradiction. A steel part can pass a one-time load test, with the stress still below its yield strength, and later break after millions of smaller cycles. Nothing about that statement means the load was secretly above the static limit. It means a one-time strength test and a repeated load fatigue test ask different questions. The first asks, can the whole part survive this peak? The second asks, what does every cycle do to the smallest vulnerable region? Imagine the same nominal force entering two coupons, one smooth, one with a small shoulder notch. The average force divided by the average area can be identical, but at the notch root, the load path bends sharply and stress lines crowd together. That local stress concentration can be several times the nominal value, depending on the radius and geometry. So below yield is incomplete unless we say where the stress was measured. A macroscopic gauge can look elastic while a tiny region at the notch slips irreversibly. Inside that tiny region, metal is not a featureless block. It is a collection of grains and defects. Repeated shear makes dislocations move, pile up, and rearrange. Favorably oriented grains form persistent slip bands, narrow planes where the forward and reverse motion is not perfectly reversible. Surface intrusions and extrusions grow. A crack can start along one of these bands even while the part still looks smooth and still passes an ordinary static check. Sandia's review of high and very high cycle fatigue describes cracks forming at cyclic levels significantly below macroscopic yield, with lives extending beyond 1 million cycles. Once several microscopic defects link, we have a crack. Pull the part and the crack opens. Near its tip, a very small plastic zone blunts the sharp edge. Release the load, and the faces close again. But closing is not healing. The new surfaces created during the opening step remain, and the crack tip can advance by a microscopic increment. Repeat the cycle, and the same sequence happens again. This is why a part can return to its original shape after each cycle, while its internal damage quietly accumulates. The crack also changes the geometry that the load sees. A blunt shoulder notch has one stress concentration. A sharp crack has a much stronger field at its tip. Fracture mechanics describes that field with a stress intensity range, delta K. For the same load range and general geometry, delta K grows approximately with the square root of crack length. The load did not get larger. The crack got longer, so the tip became a more effective lever for concentrating stress. In the middle, stable part of a fatigue growth test, engineers often use the Paris law, dA by dN equals C times delta K to the power m. dA by dN is crack advance per cycle. C and m come from material and test conditions. The important shape is not the letters, it is the exponent. If delta K rises, the advance per cycle rises faster than linearly. Early cycles may add almost nothing you can see. Later cycles add larger steps, even though the external load range is unchanged. Paris law is a regime model, not a universal promise. Near threshold, overload, variable amplitude, corrosion, short crack, and final fracture behavior need other evidence. The other familiar fatigue tool is the S/N curve, stress amplitude against cycles to failure. It is useful, but it belongs to a specimen, finish, geometry, and loading protocol. A polished smooth coupon can last much longer than a welded or notched component at the same nominal stress. Surface roughness, residual tension, inclusions, corrosion, and a crack that is shorter than the test standard can all move the curve. Even an apparent endurance limit is conditional. A component designer must ask which flaw population and load spectrum the curve actually represents. After a fatigue fracture, the surface can preserve the route. At high magnification, fatigue striations are tiny steps left by successive local crack front positions. In some aluminium tests, one striation is associated with one load cycle, and the spacing tracks the microscopic growth rate. But that correspondence is conditional. Some alloys show weak or no clear striations, and variable loading can leave arrest lines or mixed features. The real NASA specimen and fracture surface images here are evidence of what surfaces can look like, not a claim that every line counts a cycle. The practical problem is timing. Fatigue cracks usually begin far smaller than an unaided visual inspection can resolve, and they can start on an inside surface or beneath a coating. That is why bridge and aircraft rules specify access, method, probability of detection, and crack growth data. Visual inspection may be followed by magnetic particle, dipenetrant, ultrasonic, or eddy current methods, chosen for the material and geometry. An inspection interval is not just a calendar habit. It is a calculated opportunity to find a crack before its remaining ligament loses the required capability. This is not a disaster montage. It is a decision chain. In 2021, a routine inspection found a fracture along the I-40 Hernando de Soto Bridge, and the bridge was closed for repair. The FHWA account is about inspection and response, not a claim that this particular photo proves a fatigue mechanism. In a separate NTSB report, an alternator control gearshaft failure was attributed to high cycle fatigue, with intergranular corrosion cracking even though recorded vibration diagnostics were within acceptable limits. Different structures, same lesson. Normal-looking global signals do not cancel local damage evidence. So the honest sentence is not, every load is safe, therefore the crack cannot grow. It is, for this material, geometry, surface, environment, initial flaw size, load spectrum, crack growth model, and inspection probability, the crack remains below its critical size for the required interval. Design reduces the local concentration. Manufacturing controls defects and residual stress. Inspection looks where the first crack is likely to hide. Repair or replacement changes the load path. A safe load is a property of that whole system and of how often you check it, not of one number on a static test.